So how are you doing? It's good so far?
Yes, sir. Alhamdulillah.
Okay. So day by day your presence become very less. What is the problem with this? I have seen today 57 out of around 80, no? 80 students. So we are around almost 60. So 20 missing. Is a network issue or other issue? Or in the winter you are sleeping more than you study? Which one? Anyway, okay, so this is something to be discussed later. So I prepared one assignment for you, basically not one, basically two assignment for you. So hopefully will be given by tomorrow. So after classes with other section, so we'll give you the assignment hopefully by tomorrow, and your supervisor list for your undergraduate thesis will be also given hopefully by today afternoon. So few things you have to keep in mind, and please communicate with your supervisor after we announce, and then we will be talking with you in next Friday or Saturday. So I'll let you know by Europu sir. So we'll talk and discuss about few issues about the course, about the exam and everything. So in the next Friday or Saturday sometime. So let's see. Class to inform you what is coming next. And I've just heard from other department, like in your 16 batch, so they're requesting for midterm vacation. So although I didn't have anything from your side, so do you know this, or are you aware about these issues from other department, from your other friends?
So we have mailed the application to Optu sir.
Or you mailed to Oppu sir?
Yes sir, মানে Oppu sir মাধ্যমে আপনার কাছে যাওয়ার যেটা মানে সিস্টেম ওইটা করছে আর কি স্যার। Oppu sir কে ইনফর্ম করা হয়েছে।
Okay, so this means that you are also want midterm vacation.
Yes sir, yes sir.
What is the reason behind why you need midterm? After
স্যার
a
এমনি
long
তো মোটামুটি স্যার আমরা একটা ভালো সিচুয়েশনে আছি, তাও স্যার একটু কন্টিনিউয়াসলি ক্লাস হচ্ছে তো স্যার, তো সবাই স্যার ওই আবার পড়ালেখা ঠিক মতো চালাতে পারতেছে না, চাচ্ছে যে এক সপ্তাহ ব্রেক নিলে সবগুলো একটু আগায় নিতে পারলে তারপরে আবার ব্রেক থেকে এসে ভালো করে পড়তে পারবে। মানে কন্টিনিউয়াসলি ক্লাসের কারণে স্যার মানে পড়ালেখা বেশি জমে যাচ্ছে, মানে পড়তে পারতেছে না, মানে এটা বলতেছে
মানে রেগুলার পড়তেছ না তোমরা, এটা বোঝা যাচ্ছে।
অনলাইন ক্লাসে আমরা স্যার রেগুলার কেউ পড়তেছে না, এটা অবশ্য ঠিক স্যার।
হ্যাঁ, কিন্তু এটা পড়তে হবে। অনলাইন মানে হচ্ছে আমরা ক্লাসে নাই, কিন্তু আমাদের পড়াশোনা তো বন্ধ রাখা যাবে না।
অনলাইন ক্লাস স্যার মানে অনলাইন ক্লাস করে অনেকে মানে বিভিন্ন ইমার্জেন্সি কাজ করতে যায়, কিন্তু অফলাইন ক্লাস হলে তো আমরা করতাম না, মাঝে মধ্যে মিস হয়ে যায় এইসব জিনিস, একটা রিজন স্যার।
ওকে, সো আমাকে অন্যান্য ডিপার্টমেন্ট হেডরা জানিয়েছে। সো লেটস সি, উইল বি সিটিং টুগেদার টুডে, লেটস সি হোয়াট ক্যান বি ডান। Okay, so let's start. So I'm a little bit busy today, so I might be just coincide your class today. So I'm not sure how long it's gonna be. So let's say maybe an hour class today. So already 15 past 10. So we were discussing waste stabilization pond, as you know, in the last class, which is biological degradation of organic matter, or BOD, whatever we want to say, depending on the target. And we left class in the last time with with one example, basically. So have you approached the example? Have you given try? I gave you the slide also, I think. Yes. Have you got the slide?
Yes, sir.
Okay. So have you give a try the example we started in the last lecture? Have you approached it? Some of you? Have you seen this one, or we just left and you left? I think we were here in the last class. Can you see the slide?
Yes, sir.
Okay, so have you given a try for designing the waste stabilization pond by this example? Have you tried or still not? Did some of you give a try to solve this one? Yes or no? If some of you have given, then you can tell me, okay, we have tried and then we are facing this problem, or it's not any problem, we can finish. Or you haven't tried yet? Did you want me to discuss this example, or we can skip this example? You can do that, and then so that we can start another one.
Actually, maybe none of us give it a try. You have to help us out.
Then the next question is, why you haven't given tried? Is it a time constraint or something you do not understand how to do that? What is the problem? Can I ask someone? Hey, Maisha, tumi aso class e?
জি স্যার আছি।
তুমি আফটার ক্লাস তুমি একটা ওই র্যান্ডম একটা অ্যাসেসমেন্ট করবে রোল নাম্বার দেখে, ও কোর্সে কি করে নাই তুমি একটু নোট রাখবে, ঠিক আছে?
ওকে স্যার।
That is what we needed at this moment.
Yes, sir.
Okay, so let's start then. So I will quickly discuss about the exercise. In the last class we told you to do that, and very unfortunately you haven't tried, so that is not really expected. So at least you should be in a reading mood, you should be in a doing mood in your home. So because this is more on proactiveness is necessary for online classes. It's not something we just talk and we have the video and we have the class lecture notes. It doesn't really help unless or until you must be given more time than you are gave in offline classes. Online classes, responsibility of student is much more. Then we have to give a try, we have to come up with a identification of the problems and then how to solve it. So there are many issues we have to really solve in online classes. As you know, the anaerobic pond design, basically, as we discussed, is the only one equation. We can see lambda v equals to LIQ divided by V. So we said lambda v is the volumetric loading rate. It's coming from the table or coming from the equation, empirical equation we set in the last class, which is 20T minus 100. So T was given, average temperature was given 20, and we discussed also how to estimate the T in the last class. So as you can see here, 260 gram per cubic meter per day is coming here. And then putting it in this equation, since there is no primary clarifier was mentioned, so we assume that there is nothing before the with stabilization point. So total Li coming as a 350, and Q was given 10,000. In the previous slide, you can see 10,000 cubic meter per day, and 260 is the gram cubic meter per day. Then ultimately you will get the meter cube, and it's quite huge, as you can see, 13,462 cubic meter. And if we try to find out the retention time, as you can see, the retention time is basically volume divided by flow rate, and it's coming as 1.35 days. And BOD removal is coming as 56. So this is, we are doing the exercise given based on the data. We are not thinking anything about the practical aspects, like how many ponds we will design, whether it will be series or whether it will be parallel. So at this moment in undergraduate, that may not be necessary. Also, we discuss in the class how to solve these issues if loading rate is high, if it is. So as you can see, 56% removal we are expecting theoretically from the pond, and practically, obviously, after construction we have to measure. This is in a design phase, so this is 56% based on the temperature. We assume 18 degree, the empirical equation proposed by the scientist designing the waste stabilization pond. So that is anaerobic pond. It's nothing really difficult. And for facultative, we move into the second phase. Facultative is basically based on the surface loading. This also equally based on the temperature. So as you can see, the temperature was 18. So based on that, the loading rate is 216 kg hectare day. And this is the equation, as you can see, 10 Li, but as I said, this Li will be whatever the remaining. So 56% is removal efficiency, then 0.44 is remaining. So this is, that means this is after anaerobic. So the remaining portion is this 0.44 into 350, and Q will be the same as before, 10,000, and divided by lambda S. As you can see, the lambda S based on temperature. You put the temperature and then you calculated this, the loading rate, surface loading rate. And then from where you can calculate the surface area. And you can see this is a huge surface area, 71,300 square meters. And this is your retention time is almost 10.7 days or 11 days roughly, you can say, if you assume depth is 1.5 meter. If you assume even 1 meter, even higher, or smaller returning time, so will come up. Then coming into the maturation pond, as you can see, the maturation pond is coming later on, next. And for maturation pond, obviously KT is important, and KT is also dependent on temperature. In the last class we discussed. So you calculate the reflection rate, and then you calculate, there are 3 ponds basically you have. Then what we are basically trying here, so we have given 10 to the power 8 is the fecal coliform concentration is given. So this is coming from the given data. So we have one anaerobic pond, we have one facultative pond, and then we have number of maturation pond we assume. N is the number of maturation pond. And in the maturation pond, fecal coliform decay is exponential. So that's why it is 10 to the power n. N is the number of ponds. So if it can be 1, it can be 2, it can be 3. So depending on, you can give a trial or you can solve your mathematics by putting down the equation on, and you can calculate how many. Why we put n? Because we have a requirement. What is the requirement? NE value should be 10 to the power 3 or less. So then we can put 10 to the power 3 and then we can calculate what is the value of n. Or either we can give a trial like, okay, if we assume maturation point, because we already calculated 1.35 days, we already calculated 10.7 days, we do not know what is the, so there are few unknowns basically here. One is the retention time in the maturation pond, and one is the number of maturation, how many pond we are going to design. So it assumed Tm equal to 7. Now you can say, tell me like, what is the typical retention time in the maturation pond? So typically it varies from 7 days to 30 days. I mean, depending on the target we are achieving. So it's just an assumption and trial and error basically. So it assumes 7 days and then assume one pond. So when one maturation pond, so one anaerobic, then one facultative, and then one maturation, you can see that your NE value is n value equal to 1, then your 99,957. This means still greater than 1,000, because 1,000 is the requirement set by the regulation before discharge. So if we go to the 2 ponds, then still we can see that 7,201, that means still greater than 1,000. If we give the 3 ponds, then we can see that yes, it is less than 1,000 FC. That means 3 maturation pond is necessary. But in this trial and error, what you can do, you can put 10 to the power 3, and then you can summarize, and then also you can, by one single equation, you can calculate the exponent n, and that will be also coming as, I guess if I'm not wrong, 2.77 or 78, means roughly 3 ponds we have to use. So when you come into the decision, then you can calculate the area of the maturation pond, because you know this is 7 days we assume. Depth of the pond is basically 1 to 2 meter, as you know. So assume as average 1.5, then 46,667 square meter maturation pond is necessary. And then we have to final check, we have to give. We now confirm that after one anaerobic, one facultative, if we put 3 maturation pond, then we can able to reduce the BOD fecal coliform load within the range. So now, after anaerobic, we can see that BOD removal is 154 milligram per liter, but our guideline still is remaining. It says BOD concentration must be less than 20. We have to assume. Then now we have to check whether after anaerobic, facultative, and maturation pond, because anaerobic pond, you know, the 56% efficiency, but still 154. Then you have to calculate how much is we can remove from facultative, and 3 maturation pond we design. So that's why we need K1 is the red coefficient, because it's not 20 degree, so it is as you know, it is 18 degree, so that's why we need the change. So 0.3 into 1.05, it was in the theta value, if you can remember from the last class. So theta is 1.05, 0.3 is the coming from the temperature data, and this is 18. For 20 degree is 0.3. If it is not 20 degree, then 0.3 into theta. Theta is 1.05. T minus 20. T is 18. So it is coming as 0.272 per day. Assuming this, so we have now, after anaerobic, we have facultative and we have maturation. So one facultative with a 10.7 days retention time, and we have a 3 maturation pond, so Q, with a 7 days retention time, as you can see. So by this check, we can see that effluent BOD concentration is 1.6, which is significantly lower than our regulation 20 milligram per liter. That means in this case, practically, I mean, now theoretically, not practically, theoretically, one anaerobic pond with 10.7 days, or roughly, let's say, anaerobic pond of how much is coming as I mean retention period, whatever it is, that much one facultative with 11 days, and 3 maturation pond, one after another. This means this maturation pond is a series, not parallel. Same flow, one after another. 3, 1 maturation pond 1, M1, M2, M3, and then after M3, it is quite okay from the BOD demand as well as BOD demand as well as fecal coliform demand. So then finally, so the treatment series is roughly A and A to F. This means this water will go to the F. So later on, we will assume in the field condition like how many A, how many F is necessary. But here in this example, what we found 3 maturation ponds. So this means M1. So this is M1, the same as M2 and M3, and then after that, this is M2. This is M2, and then finally M3. And then it is ready for discharge. Okay, so let's say if it is a discharge stream. So now this is ready for discharge into the river stream, for example, having this barrier. So this is a kind of flow diagram, and this is receiving effluent from the directly. So it's no primary clarifier. If there is a primary clarifier, we might even reduce the load initially 25%, then 56% in the anaerobic pond. That means another 25% if removed from here, then there is a less load on the facultative and maturation pond. So so this is raw water, so raw wastewater basically. So it's coming to the anaerobic, then retain some days, and then coming to the 1.3 days, for example, let's say roughly 1.5 days or 1.5 days, and then coming to the facultative. Since facultative is the effective one, it retains in much more, 11 days, and after 11 days, then maturation pond 1, 2, 3, and all these 3 require 7 days. As you can see, the 7 days retention, and after 7 days, this goes to the ready for effluent discharge based on the guideline given. So that is basically the example we have provided, or we have discussed in this example. I mean, in the exam also we have requested you to follow this very similar steps. So you don't need to think about number of anaerobic and number of facultative ponds here, basically. So this is the example. We have a few more example I will give you as an assignment to you. But if you have any question in this, in this discussion, please discuss whatever you want to discuss, and then remaining slide we will be discussing later on. After, if you have any comments or question in this, so we can discuss. Any one of you have any question?
Sir.
Yes.
Sir, is there any hard and fast rule to consider the retention time of maturation pond?
Hard and fast.
Sir, let me explain. Sir, I was trying an example from ITN Publications book. Here I found that they are considering, they found that they will need 2 maturation pond, and the retention time was 28.96 days. According to your statement, we can consider it as the retention time, as you have mentioned that 7 to 30 days are normally taken as the retention period, but they mentioned that as we have got the facultative pond retention time as 11 days, so we cannot take it as 28.96 days. So in the conclusion, they have said that we cannot consider the retention time of maturation pond more than the facultative pond. So is it a hard and fast rule for considering the maturation pond retention time?
No hard and fast rule, basically. As I said, I mean, you can take from 7 to 30 days, depending on the climate, depending on the sunlight availability, depending on the operation. Basically, what is happening in the maturation pond, as you know, basically the BOD degradation mostly happened in the facultative pond, basically. So that is the concept. So after BOD degradation take time when facultative ponds are not really performing well. So one of the main reason why we put that statement in a way, basically, because after BOD degradation in Bangladesh, if I should say, the pathogen removal, we are not really much more concerned because this water will not be used by any sort of agriculture or anything. They will just simply discharged into the nearby stream. So there is a hard and fast rule that you maintain the DOE guideline, but before that, you know, the degradation of BOD takes time. So that's why sometimes some people prefer that. Why to keep more or less clear water into the maturation pond quite long time? So, and if there is a plenty of sunlight, there is a light intensity is very, very high, disinfection basically doesn't take much time. The only problem starts when your maturation pond is receiving water from the facultative that having still some of the BOD left or still having darkish color. So if water is relatively free from suspended solids, then in the maturation pond doesn't really need much longer time, because in a maturation pond, what we believe or what we expect basically that relatively more clear water free from suspended solid will goes to the maturation pond, and sunlight and light intensity is required just to disinfect the pathogens present. So maybe that is some of the assumption that we should not go much higher time in the maturation pond, because if your retention time is high, that means you are keeping your water quite a long time. So, but again, I mean, here we keep 7 days, maybe, for example, let's say. So if you keep, let's say, for example, 15 days, maybe then you need only one pond, for example. I mean, if retention time is high, that means more water is just coming. But in some cases, you know, keeping the higher for pathogen removal does not really produce that much satisfactory efficiency. So this is another reason. And facultative pond retention time require little bit less because there is aerobic, there is facultative, and there is anaerobic digestion also. So after complete digestion, it takes time. I mean, so that's why we keep more retention time towards the facultative than maturation. But this is not, I mean, always right that we cannot keep water more time in the maturation pond, because some of the maturation pond is also being designed as a fish culture pond. I mean, nowadays, because maturation ponds is really more clear water, so we can culture fish because BOD degradation is almost done. So that means no harmful organism present there, and there is no oxygen depletion in the maturation pond. So that's why that ponds, it can be used for fish culture. I mean, for any sort of aquaculture also. In that case, maybe you want to keep your water much more longer, but with other purposes. For example, let's say fish culture or aquaculture or something like that. So, but I mean, this is a thumb rule, I should say. It's not hard and fast. We keep more time in the facultative than maturation, basically.
Okay, sir. Thank you.
Any other question from your side? Or are you clear about the steps we discussed? Anyway, this is the simplest one. So it's not very difficult. So shall we proceed then with other types of treatment options? If you do not have any question, then we'll back to the slide again, once again. So your Maisha madam will assess later on. Okay, so let's back to the presentation again. So in our syllabus, we mostly discuss biological waste stabilization pond, but nowadays, as you can see, there are many other problems associated with this waste stabilization pond. I think before I go into the next slide, sorry, where I am. So what is the disadvantages of having this pond system, you feel? So after solving this exercise, what do you feel? What sort of disadvantages of having this pond system?
Sir, it needs a huge space and lots of time.
Hey, Roman, অনেক বলেন 11:30 দিকে আমার একটা ফোন দিতে। আমি ক্লাস নিচ্ছি তো। 11:30 দিকে আমাকে একটু ফোন দিতে হবে, হ্যাঁ? আচ্ছা। এটা কি দিছে বিল? হ্যাঁ, ওনাকে একটু মার্ক করে দিতে হবে। তৌফিক সাহেব আছে? জি। হ্যাঁ, বলছে 11:30 দিকে স্যার ফোন দিতে বলছে ক্লাস শেষে, হ্যাঁ? আচ্ছা। ওরে এগিয়ে তৌফিক স্যার আছে? Sorry. Yeah, so as you can see that these require quite long treatment periods, as well as huge land area requirement is there. And also we require sunlight, we also require air, so that means we require temperature. So that is something which really sometimes difficult in urban area, number one. Number two, you know that sometimes it's difficult in a cold climate region. So it's very, very difficult. And almost you can see in the exercise we have just completed. You assume the how long is necessary? 11 days, then 7 days, 18 plus 90, almost a month required to deal with 10,000 cubic meter with a huge land area availability. I mean, that is sometimes is quite long. So ponds usually require lengthy treatment periods, weeks for facultative, days for aerated system. All the facultative system have been very little mixing other than inflow, gas bubbles, wind effects, long retention period. Okay, so that is what is necessary, but it is sometimes really difficult. Then what is the next? As in any mixed system, the contents have the same concentration as the overflow. This means that the organism in the pond continuously experience a low level of substrate to feed on, which slows down the treatment considerably. What it says, sometimes, you know, the one pond from other pond, because it depends on the bacteria, and then bacteria needs the food. So if organic matter concentration goes down, that means obviously BOD goes down. And if BOD goes down, that means there is not enough food for your bacteria to survive. So sometimes without food, bacteria cannot grow up. So it's difficult because after anaerobic, mostly coming into the facultative, and after facultative, there is less amount of substrate or less amount of organic matter or less amount of BOD. So this is something researchers thought of, like, you know, using multiple ponds or using some sort of aeration. reducing the land area availability. They're thinking of what can be done basically if we want faster degradation. So faster degradation means we have to balance the mass of food supply as well as bacteria. So it's a kind of mixing with your old sewage with fresh sewage continuously. So it's a kind of a mixing. So some of the young bacteria, some of the old bacteria. So it's a kind of mixing. So that is some idea putting into the one container, for example, and giving the oxygen by mechanically will help much faster degradation, and it can reduce drastically the time required by the pond system as well as the land area availability, but which required more skilled way to treat the wastewater with necessary quality necessary. So it means that it's more skilled type of treatment. It's natural, but still it's semi-natural, I should say, because it's more mechanized and treatment natural, obviously, but it needs a lot of input from the skilled people, a lot of input from the machineries, a mechanical way of treating. But less retention time, faster degradation, and less requirement of the land area. So this is what is in the next type of, I should say, another type of biological wastewater treatment, which is now very popular in developed countries as well as in developing countries, because we are also facing problem with designing the pond system in basically in the sewage treatment plant. Even in Dhaka and Chittagong also, so pond system require a lot of land area. So that's really hindered the design system. So in that case, they try to put the activated sludge process. The process, as you can see, is a activated sludge. This means sludge. This means that food or organic matter we try to activate in the tank system. So we are not going to design the activated sludge process because that is not the scope in this syllabus. But you should know what advancement being made and what is coming next. Maybe we have to really focus more on activated sludge than WSP nowadays because of the land availability. But still, the pond system is, in terms of operational maintenance, in terms of construction, that is the cheapest option possible to naturally clean the wastewater. But activated sludge, as you can see here in the diagram, so you receive the raw water. So you receive the raw water in a tank we call aeration tank. Is completely closed. It is not open. It's a closed tank, and we put air by mechanical diffusion. So air will be put. I have a few other slides also from the master's course. So I will just show you the slide, but that is not really required, just to make you understand much more better. So what is happening now? Then this is you receive the raw wastewater from the primary clarifier, or if there is no primary, then obviously coming here. And then what we are doing, we put aeration mechanically, so it's a lot of diffuser or bubble. Sometimes we keep tank open also, sometimes it's closed container. And then after giving the aeration or aerobic bacteria, faster degradation, mixing all together, then we, after let's say about 30 minutes or 40 minutes or an hour, or maybe let's say 24 hours, then we put this one into a clarifier. Clarifier means this is the same as the primary clarifier or sedimentation basin, where just only settlement or sedimentation will happen. So after the passing the clarifier, there is the fresh sludge coming at to the bottom, as you know, the sedimentation techniques. More clear water as going as a treated water, to the discharge stream or in the tertiary treatment for pathogen removals or whatever. But this sludge has a two component. One, we goes to the sludge treatment, or another part, we put it into the aeration tank. That means, so let's say this is a Q. Okay, I will show you the slide. So this is Q, and then this is coming as QW, underflow. So, and then this is a mixing of old sludge from here and mixing of new sludge here. So that means there are different sludges, different foods, different bacteria. So that is basically the concept. So this recycle, raw wastewater, mixing together, few dilution, few matured bacteria, few old bacteria, few young bacteria. So all three types of bacteria, different types of food coming here in presence of air, the faster degradation is happening. So that is called activated sludge. This means you try to keep sludge activated as many cycle as possible for faster degradation. And then you take sludge out from the system, and then you take treated water out from the system. So that is basically the philosophy of activated sludge. And there is a little bit more elaborative example, a slide. So as you can see, Q and X0, this is what is the concentration and flow. You don't need to think about that. Coming as aeration, you give mechanical diffusion, goes to the clarifier, sludge is going out from the system, and this is called return activated sludge. Few sludge we back to the system, as I said, to make relatively young, matured, and then old bacteria for faster degradation. So this is the system boundary. This means this is a control system where we control the airflow, we control the concentration, we control the design flow Q. Everything is controlled in your hand in the design, and then you produce the faster degradation. And then this is a kind of removal efficiency. As you can see, in the primary clarifier, primary target is suspended solids 50 to 80, BOD 20 to 40, but 20 to 40 is very relatively high, so it's not possible. Up to 30%. Phosphate, nitrate is very low in primary. E. coli is even low, 1 log. So as you can see, E. coli is much faster in the tertiary, even little bit moderate in the secondary, but secondary BOD concentration you can see 70 to 90% BOD we remove in the secondary. So secondary is primarily for BOD, and SS is primarily for primary, and phosphate and nitrate also is possible to remove in tertiary, moderate in the secondary, but E. coli required tertiary. So that is sort of typical removal efficiency we have achieved in the activated sludge system. So if I just stop this slide now, just to take you to the another very quick slide. And let me show you in a 10-15 minutes time. So just to give me a time, that is for basically we discuss in the master's level. So I think I should have this slide here. Okay, so I'll just show you the system dynamics, which is much more complicated, than the system we discussed in the. So can you see the slide? Is slide visible to you?
No, sir.
Can you see now?
Yes, sir.
See now.
Okay, so this is total slide. As you know, this is okay. This is under the suspended growth system. We call suspended growth system organism. That is also under the WSP as well as the activated sludge system, and attached growth system we'll discuss later. We have in the syllabus fixed film system. So we'll be discussing in the next class. Attached growth system trickling filter we'll be discussing more detail. So we just skip it at this moment. So we'll show you So I have another slide for typical slide for undergraduate. So I just show you. So this is, I'm taking from master's level course. So this is the activated sludge, basically what is happening, how basically is coming from primary clarifier. Then you can see that the air is imposed through the air diffuser. So this sludge is always in a mixing mood, something like that. So more bubble you can see, more flotation, and then it's coming into the settling tank, and the settling tank more sludge or mixing of sludge, basically mixture of sludge and liquid is basically on the bottom, and relatively clear water into the top, and this clear water is going out for chlorination or any sort of disinfection or maybe for discharge. And this is pump from the underneath, and this pump has two components. Sometimes we give it back to the going to the sludge digestion system, and also another part is going as a return activated sludge again back to this chamber. So it's just mixing of fresh sludge with other sludge necessary. So text, we just remove it just to make sure that we design parameter here is used FM. So don't confuse with your FM with this fineness modulus. This is basically food to microorganism ratio. So F is the food, M is the microorganism is the bacteria, and food is the BOD, as you know, or organic matter basically. So food is organic matter, but we measure in terms of BOD. And M is the volatile suspended solid concentrations, where only microbes or microbial activities is happening. So this is called the food, or sometimes we call MLSS, mixed liquid suspended solid. MLSS. So this is really difficult thing. So here are a lot of equations, how to stabilize this. There is a model available, but this is more, or I should say, technical aspects is there. So as you can see, this is quite difficult equation and everything, but it's not difficult. Obviously, we need to learn this one first before we become expert in the activated sludge system. But activated sludge system is also, I mean, I should say, I mean, nowadays is very popular in the design of, I should say, secondary wastewater treatment, because you can reduce the significant amount of land area requirement, and that is not under the nature. You know, sometimes you depends on nature, and nature is not in your control. So basically the thing is that is not in your control. So nature controls itself. So self-control of nature. But if we try to control by ourselves, then we design the system where we control the oxygen supply, where you can control the microorganism supply, where you can control the food supply. So in that case, it's much more technical. This means something I design, I know how to control it, where to control it. So that system basically we call activated sludge system. So that activated sludge system is now very popular in biological wastewater treatment with a relatively faster degradation possible with a minimum retention time. So that's why, so activated sludge is normally, we can see that around 30 to 40 minutes of retention time, if we can do that, obviously in a small scale. If it is a big project, not even greater than, I think, 24 hours or maybe 2 days maximum of mixing. I mean, if it is open tank, sometimes activated sludge is also keep open just to take some oxygen from the atmosphere, and if necessary, then you can do the mechanical mixing. So that is a kind of hybrid. So in that case, it is open system, or you can do it in a controlled environment. So both are possible, but if we can try to keep it little bit, I mean, I should say little bit natural, I can say. I mean, you can assume that sunlight and oxygen is available in Bangladesh. I mean, obviously we are in a situation, then why to keep the system closed? So we can keep the system open. so that we can take help from the environment, like sunlight, as well as the air, for example. In that case also it is possible in inactivated sludge. But inactivated sludge, which is not possible to culture the algae, which is possible in the pond system, and algae produce also oxygen. So in the activated sludge only, we have to give the oxygen externally. So there is no algae present in the activated sludge, so that it can help to produce the oxygen. So a pond system is, I should say, is the maintenance and whatever you can say is much more less in compared to the activated sludge system. But activated sludge system has a lot of advantages compared to the pond system, where sometimes, even though higher operation and maintenance cost is involved with the activated sludge, but depending on the retention time, depending on the land availability, nowadays is very popular. The activated sludge system, where you can make the balance of food and microorganisms. So you can maintain how much food is necessary, because if I'm the bacteria, if you are not giving me the supply, then obviously bacteria will die. And if bacteria die, then producing the colony of bacteria, which is required for organic matter degradation. So sometimes organic matter is very high compared to bacteria present. In that case, degradation is very slow. If degradation is very slow, in that case, hydrogen sulfide formation, bad odor producing, and also higher retention time are necessary. So that is something why nowadays activated sludge is being preferred compared to the pond system. But pond system still popular in the developing countries, where construction cost, land availability, operation and maintenance is really a big issue. As you know, in Bangladesh, we maintain everything, we design everything very nice, but we do not operate. So operation and maintenance is very, very difficult, which is not the case for developed countries. They have money, they have budget, they have a better operation and maintenance. And also in activated sludge treatment approach, with the, in a treatment plant, obviously required a lot of skilled people in present day-to-day basis in the treatment plant, because activated sludge maintenance of a very good food FM ratio around, let's say, 0.2 to 1.5, roughly the ratio. Maintaining of this food microorganism is very, very critical and require a lot of technical knowledge about the biology, as well as the design, as well as environmental chemistry. So using a lot of equations you have seen, maybe just in a glimpse in the slide. So that is sometimes we fail to maintain. But if you go to the industries, for example, textile industries or garments industries or any sort of other industries, nowadays they are mostly designed the activated sludge system than pond system, because pond system require quite a huge land area. So industry is always compromising the land with their wastewater and then their production. Obviously, land is really a vital issue. So in that case, the activated sludge system becomes much more popular. And both activated sludge and waste stabilization pond system are, we call, this is what I should say, suspended growth system. Suspended means bacteria grow in a liquid or suspension. So it's always in a floating condition. And there are other approaches we call attached growth system, which is also in the syllabus. I was planned to discuss today, but I can't discuss today basically. I have other things to do today, so I have to short your class, that's why. So that is basically, I should say, in the attached growth system was also popular in developing countries than developed countries. But attached growth means you give the surface to grow the bacteria, and bacteria can grow anywhere, even it is concrete, plastic, it's a brick, whatever, anywhere bacteria can grow. So that is one of the advantages of, if they have the food, if they have the environment, if they have the moist condition. If it is not completely dry, then obviously bacteria can grow and survive. So that is concept of the fixed growth system. So fixed growth means, then obviously we can see that bacteria can grow anywhere. It can be in the water, what we can see in the pond system, like anaerobic and facultative and maturation, we can see always water is in dynamic process. So it's not fixed anywhere. If we allow, okay, this is the place only bacteria can grow. So that is called fixed growth system. So fixed growth system is basically trickling filter system. That system we'll be discussing in your next class. And this trickling filter is also in the course. So in the suspended growth system, WSP, waste stabilization pond, is in the syllabus, but activated sludge system also, we have the content, but content is much more, you can say, the more generalized, like comparison of activated sludge with waste stabilization ponds, and how these two systems basically differ with their advantages and disadvantages. So this is from today's class basically, so in the activated sludge as well as in the pond system. So now it is a time for discussion. We can discuss around 4-5 minutes. Then I will hand over to Maisha. Maisha will discuss about the exercise we have discussed. If you have any question, one by one, you have to solve it and you have to fix it up, how you want to solve it. But before I left, any question or any comments from your side? Hello. Anything about activated sludge system? So if you want to know a little bit more, or whatever I discuss about activated sludge, if you are not still clear, so can you please discuss with me? Hello. এই আছো তোমরা? শোনা যাচ্ছে?
Yes, sir.
হ্যাঁ, বলো, অ্যাক্টিভেটেড স্ল্যাশ সম্পর্কে কিছু জানার আছে? বাকিটা তোমাদের ইয়ে করবে, ওই মাইশা ম্যাডাম ওই এক্সারসাইজটা একটু আলাপ করবে আজকে ফাইনালি ক্লাস শেষ হওয়ার আগে। আমি যে অ্যাক্টিভেটেড স্ল্যাশ সম্পর্কে একটু কুইকলি গো থ্রু করলাম, এই বিষয়ে তোমাদের কোনো কিছু জানার আছে? No question. Okay. মাইশা,
জি স্যার।
তুমি একটু র্যান্ডমলি ওদের ওই যে অঙ্কটা একটু ওরা একটু নিজেরা করুক, তুমি একটু 5-10 মিনিট একটু জাস্ট তুমি র্যান্ডমলি রোল কল করে তুমি ওদের থেকে একটু জেনে নিবা
ওকে স্যার।
কি করেছে। আর আমরা একটা অ্যাসাইনমেন্ট রেডি করে আমরা কালকে বা পরশু ওদেরকে দিয়ে দিব। ওদের অ্যাসাইনমেন্ট দেওয়া হয়নি তো?
Okay, sir.
তুমি একটু আমার সাথে কথা বলে নিও, হ্যাঁ?
আচ্ছা, স্যার।
ওকে, ঠিক আছে, থ্যাংক ইউ। তাহলে আমি লগ আউট করছি না, তুমি যতক্ষণ আসো ক্লাসে তুমি শেষ হইলে আমাকে বলিও।
ওকে,
আমি
স্যার।
আমি আমি অনলাইনে থাকতেছি, ওর অঙ্কটা করুক, হ্যাঁ?
ওকে, স্যার।
আচ্ছা, ওকে, থ্যাংক ইউ।